All right, we'll continue with our finite dimensional weak form, and recall that we're actually doing things in 3 dimensions, right? So that aside that you've probably experienced in the previous segment was only to give us a little more insight into the basis functions. So return to the finite dimensional weak form. Right, and let's recall what that is. It is the following: integral over omega wh comma I jhi dv equals integral over omega wh f dv plus, or sorry, minus integral over the Neumann boundary wh jn ds. Okay, so this is our finite dimensional weak form. Of course, we already have over this our partition into element subdomains. All right, so what that allows us to do is recalling that partition, which is that omega equals the union of omega is the union over E omega E, right? What the above integral gives us, right? The above integral equation gives us is the ability to write it out as a sum over the element subdomains, right? So it's a sum over E integral over omega E wh comma I jhi dv equals sum over E integral over omega E wh f dv plus sum over now let me use a different set here for the sum, okay, and I'd like you to think about why I need to use a different range for this last sum. Okay, remember that now it has to be over elements that have a surface coinciding with the Neumann boundary. Okay, wh jn, and I've got to be careful with signs because this is not a plus, it's a minus. Okay, ds. Now, I'm going to say here that it's a sum not over all the elements, but over E belonging to E sub n. Okay, sorry, belonging to, let me make that really a set. So let me make that a script E. Okay, what I'm saying here is that E belongs to the set E sub n if the boundary of element E intersection the Neumann boundary, okay, is not equal to the empty set. Okay, right? So all this means is that we're considering elements that coincide with whose surfaces coincide with the Neumann boundary. Okay, so we return to our continuum potato, or maybe we should start calling it our football now, right? Right, and I'm showing you the Neumann boundary, the blue part of the boundary. This is our basis, right? So any element that has a surface coinciding with this surface is included in the set E sub n. Okay, all right. So that's the sort of notation we're using here. So let me just draw that here. Right, so we have an element, we have our domain, right? And I think we have been denoting that as the Dirichlet boundary. This is the Neumann boundary, right? So we're talking of an element that could have a boundary coinciding with this Neumann boundary, right? Or that does have a boundary coinciding with the Neumann boundary. Okay, so this is an element, say omega E, right, where E belongs to this set. Okay, and it is only over that set of elements that this very last sum is computed, right? Okay, so we have this setting. Let's then stare at this finite dimensional weak form and note that we do need to compute some gradients, as we've had to for the one-dimensional problem, right? We need to compute gradients there as well as for this term, because we remember that JH of I is just minus kappa Ij UH comma J. All right, so we need gradients as well. Okay, so in computing gradients, let me just state this, we need function gradients, right, which is not a surprise. We needed the same things in the 1D problem as well. Now, I'm going to take a step here that will make our notation a little more concise, okay, and what that involves is the following. I am going to take this, the vector xi eta zeta, right, and write it as simply xi1, xi2, xi3. Okay, this is exactly the way in which we are writing our physical coordinates as well. All right. Okay, this is just as we're saying x, physical position of a point, is x1, x2, x3 in terms of its physical coordinates. Okay, this is going to save us some space and just give us a briefer type of notation as we get further into the development of the weak form. All right, it's going to be immediately clear why we need this sort of thing. Okay, so now we need to consider UH over element E, comma I in general. Okay, this is sum over A going from 1 to number of nodes in the element, NA, comma I, D, A, E, right? And the same thing for WH. WH, E, comma I is the sum over the nodes in the element, NA, comma I, D, sorry, C, C, A, E. Okay, so we need to compute these gradients of basis functions. All right. What I am going to do here is leading up from the notation that we've already established for the coordinates on the parent subdomain, I am going to say that we will use uppercase indices for components of Xi, okay, for Xi in, sorry, okay. All right, what this means is that the components of Xi we are going to write as Xi I, where we're using an uppercase I running between 1, 2, and 3. all right? Okay, so using that and recalling that the way we are developing our basis functions is to parameterize them in terms of the coordinates in the parent subdomain, we have quite clearly NA comma I, which after all is just partial of NA with respect to xi, right? We are going to write this as partial of NA with respect to xi, capital I, and using the chain rule we have this. Okay. What we have implied here is a certain convention. Do you know what that convention is? We've applied a certain convention to one of the indices here. Right? Of course, we are implying here that there is a sum on I equals 1, 2, 3. Right? This is the so-called Einstein summation convention. Right? We will use that repeatedly. Okay? All right. Now, this is straightforward for us to calculate, right? And I'm actually not going to go and write it out again, right? Because we know each of the NAs in terms of the corresponding X's, right? Xi1, Xi2, Xi3, which were formerly our Xi, eta, and zeta. Okay? So, just remember that we have right. So, we are talking of taking this derivative with respect to a particular xi, right? That I may be 1, 2, or 3, right? We've written out the shape functions, we know how to take those derivatives, right? Straightforward. Now, the thing that remains to do is to figure out this quantity. Okay? Right? How do we get that?